where we had said that if you need the time, if there is heat transfer, you need the time. And if the time is very large, then it means that there is enough time for heat transfer. So if there is enough time for heat transfer, the environment temperature will be approximately the same as the body temperature at all times. Okay. So now we can move on to solve the example. So we have finished the first part. A is okay. Now it says that to calculate the final volume and temperature, assuming constant specific heats for both cases. So I will first start with the Q is 0. So for the B case, I will start the B case. So the question says that it is reversible, this one, and constant specific heats. But these are two famous clues given in the question. So I will add it here. So that constant Cp and the Cv. This is the first one. And you have also, what is the first one? Reversible. Now let me write the given values here so that we can see what's going on. Volume, initial volume, volume 1, let's say, it is 30 centimeters cube. Erase this part. So initial volume V1, it is, because it is fully extended, okay. So, and since it is in fully extended form, it will have the pressure as the pressure of the environment. It will have the temperature as the temperature of the environment. So let's write it now. So P1, it will be environment pressure, and the temperature 1 will be 25 degrees Celsius. This is for the first stage. And the next stage says that the pressure rises to 290 kilopascal. P2 is 290 kilopascal. And we don't know anything about the next processes. We don't know anything here. We don't know anything here. Okay, so the ideal gas law doesn't help us because for the second stage, we don't know any. So to find any property, you need to know two of them. Okay, Gibbs phase rule, if you remember it, the Gibbs phase rule says that okay, you need to know two properties. You need to know two properties and to find any third one. But for the first stage, we know two properties. We can find any third. But for the second stage, I don't know any two property. Therefore, I don't have any option to find the final volume. And it says that final volume and temperature. So V2, we should find it, and P2, we should find it. I will first start with the quick process. And if it is quick process, then you will have the Q will be equal to 0. Okay. Now let's solve it. So I will write the second law of thermodynamics. Okay. For the second law of thermodynamics, you will have the change of entropy of the system. Okay, will be equal to total in minus total out. Okay. This is the second law of the thermodynamics, and since we know that plus also generation, sorry for that part, plus also generation. And in this question, Q is, so for in and out, if you remember, for the entropy balance, for in and out, we have two options. So we have the Q and we have the mass. Similarly here, we have the Q and we have the mass. And for the bike hand pump here, the Q is 0, we have said it is the fast process, Q is 0, therefore it is 0. And also, the process is closed system because the question says, so you are holding your thumb over the exit of the pump. See it? So you are putting your thumb here. Okay, so it means that if you put your thumb here, it means that there will not be any mass transfer. So therefore, this one is 0, since we are holding our thumb. Okay, so that mass transfer is 0, closed system. It is closed system since we are holding our thumb on the exit of it. So therefore, these terms here, they are 0. Okay, 0. Now comes the generation term, and the generation term is the creation of entropy, and if the process is reversible, you see, that these are the assumptions that we are going to use. If the process is reversible, reversible means ideal, and ideal means no entropy generation. So if there is no entropy generation, then it means that this term will be also 0. Okay, so the change of entropy of the system becomes 0. So let me add it here. The change of entropy of the system. When I say system, it is handheld bike pump. So it is bike pump. This is our system. Let me show actually our system here. So our system is the pump itself. This one. So actually, I should include the outlet part because I don't want any mass transfer out of the system. So therefore, you should have this. This is our system. It is air only, air. Our system is air only. So therefore, what I will do now is that bike pump and air. Our system is bike pump, which includes air only. Okay, air only. So it will be equal to 0. So if it is 0, then it means that S2 minus S1 is 0, or S2 is same as S1. Okay. I've said it in our first lecture. So if you have the T1 same as T2, we call it as the, for example, isothermal process. But if you have the S1 same as S2, we call it as isentropic process. And now let's solve when the S1 is same as S2. Let's go back to our formula sheet here. We can see the formulas here. So we have the ideal gas. Now we are going to use ideal gas, not incompressible substances. Ideal gas. We have two options, constantly specific heat and variable specific. Of course, we are going on that way. And that for that constant specific heat, we have the two options. We need to find entropy change. In this question, entropy change is not required, and we should go to isentropic case. You see, for the isentropic case, we will have the three formulas here. Okay. The temperature ratio is equal to the pressure ratio. So you have this one, or that one, or that one. Whatever option is best for our case, we will use it. Okay, so in our case, T2 and the nu2 is unknown. These are unknowns. Okay, therefore, this formula doesn't help. And the T2 here, it is okay, but we don't have any unknown here. Therefore, we can use this option. And the P2 is okay, P1 is okay, and nu2 is unknown. Therefore, we can use this option. So with the second formula, we will find the T2. And with this formula, we will find V2. You see, the second formula will help us to find the T temperature at the second stage, and the third formula will help to find the volume at the second stage. Let's do it. So I will write the formula now to find the T2 here. So you see, it is T2 is unknown. So this one is in our case. So let me write the formula here because I don't know it by heart. So that P2 by P1 is P2 by P1, K minus 1 by K. So T2 by T1 will be equal to P2 by P1 to the power of K minus 1 by K. Okay, this is the formula that I'm going to use. And for this formula, I will just write the values here, that the pressure at the second stage, it is given in the question. It is 290 kilopascals. At the first stage, it is 101 kilopascal. And the K value, which is Cp by Cv for air, is 1.4. Therefore, I will write the 1.4 for Ka value. And the T1 value is the 25 environment, it is given, plus the Kelvin scale temperature. If you solve this equation, I will just give the final answer to you because we don't have enough time. So T2 becomes 402 Kelvin. Okay. We have found the T2. Now it is time to find the the volume at the second stage. So to find the volume at the second stage, I will go back to the formulas here. Okay, so that you have the P2 by P1 is V1 by V2 to the power of K. So P2 by, write it, P2 by P1 will be equal to V1 by V2 to the power of K. So you can, let me write the value here. So 402 Kelvin. Okay. Now you see, I have two properties. I can find any third one. Okay. So it means that you can use this relationship. It is okay. And also, or the Gibbs phase rule says that it is okay now that you can find any third property. So by using the chart, or you can use the PV's MRT. You can use PV-MRT relationship to find the volume at the second stage, or you can use this relationship. And to find the mass, for mass, you have to use this one is P2, V2, MRT2, and to find the mass, you'll have to use P1, V1 is MRT1. You have to use first relationship to find the mass, and then you replace it back to here. Or you can use this formula, which is easier for our case, and I will write this one as a 290 divided by 101 will be equal to V1, which is V1. Where is V1? Is 30 centimeters cube divided by the V2 and to the power of 1.4. If you divide and do that calculation, you will have the V2 value. I'm just writing it, which is 14 centimeters cube. Okay. I've finished this part. And the V2 is 14 centimeters cube. This is for the quick process option. See, the process is quick, Q is 0, generation is 0 because it is reversible, and then you will have this final result. Now comes the, if the process wasn't quick, so let me add the second option here. If the process is not quick, okay, so very slow process. In that very slow process option, you will have the temperature as constant value. Temperature will be constant, and if the temperature is constant, then you will have you will need to use the ideal gas relation, which says that PV is MRT. Okay. Let's do that now. So if the, sorry, so 1 minute, I should. So the process is very slow process. In that case, T is constant. If T is constant, I've said it in the previous case, the temperature remains constant. I've explained it here. So then you will have that the P1, V1 will be equal to MRT1. So therefore, M is constant, R is constant, T1 becomes constant, which is 25 degrees Celsius, or 25 plus 273. And from here, you will find the P1, V1 is constant. Okay. If I do this similarly, for example, P2, V2, it will be equal to MRT2. And since T2 is same as T1, so it will be MRT1, and it will be again constant. Okay. The same constant here. P1, V1 will be equal to P2, V2. So P1, V1 will be equal to P2, V2. And from here, you will find that V2 will be equal to, and solve that equation, 10.5 centimeters cube. Okay. So this is the second case. So what we have done for the example is, we have calculated the final volume and temperature, assuming constant specific heat value for both cases. One is that it is very quick, I've done it, and the second case is that it is very slow. For these two options, we have found the final volume and the final temperature. If it is very quick process, Q is 0, adiabatic process. And if I apply the second law of thermodynamics, I will have this relationship and entropy remains constant. If entropy remains constant, I can look at the formula here and I can find the final value. Okay, I've just used the formula from the first slide. But if the process is very slow, which is the second case, then the temperature remains constant because at the very slow rate of the heat transfer, you have the constant temperature you have very small actually temperature difference between the environment and the pump. And we can assume that they are almost the same. And therefore, from this relationship, I can find the final value. If you have questions, you can ask. Otherwise, I will move on to the next example and solve it. Okay, there is no question. Good. So I'm going to the second example here. So I have a steady running computer chip here. This one is steady running computer chip. These terms are the hints. They are very important. Okay. And shown above and has a surface temperature of 50 degrees Celsius. So this computer chip, it has a temperature of 50 degrees Celsius, which is its surface temperature. And the ambient air is at 25 degrees Celsius. So there is an ambient environment which has a temperature of 25 degrees Celsius. When the chip runs, it dissipates 2 kilojoules of electric work supplied. So what happens is that when the chip runs, it will give off its heat to the environment with the amount of the 2 kilojoules. Okay, and find the entropy generated in the chip. What is the amount of generation of entropy? So this term is very important. Generation, I've said in our previous lecture. So it means that the creation. Okay, new entropy is created. It is very different from energy. Okay, for example, when we say energy, energy is constant. When we say energy, it is constant. But for the entropy, it always increases. For total. For subcomponent, it can decrease. For example, say that this is the system here. You have two components. Okay, this one may have delta S less than 0, but this one is delta S, let's say 1. And but delta S total, which will be equal to delta S 2 plus delta S 1, it should be greater than 0. Okay, this one always. At the minimum case, it can be 0, which is the reversible case. Okay, now we have this process here, which has a surface temperature of 50 to infinity 25 degrees Celsius. Now we have to find the entropy generation. So to find the entropy generation, first I need to select my system, which will be the chip itself. So yes, so I have the system which will be chip here. Okay, I'm taking the dashed lines around it to see that. And it has a temperature of 50 degrees Celsius, and it is constant. Okay, the boundary is at 50 degrees Celsius, or boundary temperature is 50 degrees Celsius. Boundary 50 degrees Celsius. And there is an amount of 2 kilojoules of heat transfer from the system. Go back to here. 2 kilojoules of dissipates. Dissipates means this is out quantity. So you will have the heat transfer out of the system in the amount of the 2 kilojoules. Now I'm going to write the second law here because I'm trying to find the entropy generation. So I will write that the delta S of the chip will be equal to total in minus total out plus generation. Okay, this is the equation that I'm going to use. This is not a new equation. I've said it multiple times. This is from equation set here. The equation set. This is for the first law, and this is for the second law. Okay. I'll go back to our example here. So the first, it is steady. If it is steady, this term is 0. So since steady. Okay. And in, it can be by heat, it can be by mass. Out, it can be by heat, it can be by mass. And for our system, these two terms are 0 because closed system. And since it's a closed system, then we cannot have any mass transfer. Chip is a closed system. And now comes the heat transfer. The heat leaves the system, okay? And if there is no heat transfer into the system, therefore this term is becoming 0. But we have this term, I will write it. And the generation term, it is not 0, therefore it also leaves. So what you will have is that if I write the full form of the, so that the balance of entropy, so instead of the Q, actually it is Q by TB, and instead of the Q here, it is Q by TB. This is the full form, but the equation says that it is Q and the, so therefore I will write that 0 will be equal to 0 minus Q out divided by T boundary and plus the entropy generation. Okay, so that the heat transfer that leaves the system, it is 2000 joules, and it leaves the system from 50 degrees Celsius. You can see, therefore it will be 50 plus 273, and therefore the generation of entropy will be equal to, so the final answer is 6.19 joules by Kelvin. This is the generation of entropy. Okay, so this is the equation. Okay, so when I say that it is by heat transfer, it is not Q itself, but it is Q by temperature. If I go back to the previous slide here, you can see what is the equation. So you see it is the heat transfer by temperature, okay, not the heat transfer itself. But for energy, it is the heat transfer alone. So therefore, you should be careful here. Okay, so this is the amount of the entropy that will be generated inside the chip. Okay, so this chip will always generate this amount of entropy. Okay, so we have finished that part. And in the chip, this one is the first part, and also outside the chip. Now we'll find the outside of the chip. So for that case, so I will say that we have the chip here. Okay, and here you have the temperature which has 50 degrees Celsius. And then the temperature at around the chip is less than 50, but it is not the environment temperature. But I'm leaving a boundary, something like this one. And here the temperature is 25 degrees Celsius. Okay, but here you don't have the 50, but also you don't have the 25. Okay, this one is the environment. Okay, so then you will have the heat transfer that crosses the boundary here. So if it is 25, then it means that there is some more temperature here because the heat leaves the system Q. It is 2 kilojoules. Okay, and since it is steady, then it will leave the system out of it. Okay, you will have the Q, 2 kilojoules of the energy transfer from the system. Okay, so if you do that, so this 2 kilojoules of energy leaves the chip and the plus this surroundings part here. Okay, now I will write the second law for these two components here. So second law again, it will be that del S, so of the total here. Total means that chip plus this part. Okay, let me call it as the surroundings. Chip plus surroundings will be equal to that in minus out plus the generation. Okay, I've said it that in term can be by mass. In this case, it is closed. It can be Q, no heat into the system. Can be by mass out, there is no, and the Q is there. generation is there, and delta S surroundings is also there. So therefore, you will have the delta S total will be equal to that. You will have the so this one also is 0 because it is steady, and therefore you will have 0 will be equal to in part, which is 0, minus the Q out, which is 2 kilojoules, divided by the boundary temperature. Okay, in this case, the boundary temperature is 25 because I have included the chip plus surroundings where the temperature drops to 25. Okay, so therefore I will write the temperature here as 298 Kelvin, or it is same as 25 plus 273, and this one is also 2000, and plus the generation part, of course, the entropy generation. And if you solve that, you will see that the entropy generation will be equal to this one, 2000 divided by the 298. It will be 6.71 joules by Kelvin. Okay. So here for the chip, we have solved it. For the chip, it is 6.19. Write it here. For this one alone, the entropy generation was, I've written it here, 6.19. Okay. For the chip plus the surroundings here, let me use different color. This one and all of it, let's say that all of it here, the chip also is included. Here you have the entropy generation as the 6.71, okay, joules by Kelvin. So therefore, if we exclude the chip, so if exclude the chip, then you will have the entropy generation will be equal to 6.71 minus 6.19, and that one will be equal to 0.52, 52 joules by Kelvin. Okay, this is without the chip. Okay. If you include the chip and the environment, it will be that 6.19, so 6.71. If you find for chip alone, it will be 6.19, and between the chip and the environment, it will be 0.52 joules by Kelvin. If you have questions till this part, you can ask. So, okay, there is no any question, so I'm moving on the next one. So the question says that we have the hot combustion gases at 1450 Kelvin. So they enter the car engine block through its surface, which is at 430 Kelvin. So we have the gases here. Temperature of the gases is, this one is 1450 Kelvin. And the temperature of the surface of the engine block is at T surface is at 430 Kelvin. And the engine block receives 2 kilowatts of power. So you have the 2 kilowatts of power that comes from the gases to the engine block. And then block transmits this power at its 400 Kelvin surface to the cooling water. So then it receives the temperature of the 2000 watts from the 430 Kelvin. Then it gives this temperature to cooling water. Is here, it is cooling agent. It is glycol, and it has a temperature of 400 Kelvin for its surface. Okay, and the cooling has a temperature, so glycol, this one has a temperature of that 370 Kelvin. Okay, so that for the energy transfer. Okay, so then you will have this glycol at 350 Kelvin delivers this power to the air, so that when it comes to the deliver of the airflow here, this one is the radiator. Okay? So when it delivers air, then it will have the temperature of 350 Kelvin, and the air will have a temperature of the 23 degrees Celsius, or will be added to 96 Kelvin. Okay, so this is the system. So if we summarize it, so we have the engine block here. Okay, this is the engine block. This engine block will have a temperature of 430 Kelvin. It receives 2 kilowatts of heat, and then it has 2 kilowatts of heat, and then it delivers these 2 kilowatts of heat on its surface where you have 400 Kelvin. And then from this part, when engine block ends, you will have the glycol part. For the glycol part, this heat from the engine then is transferred to glycol. You will have the 370 Kelvin on one side of it, and then you will have the 350 Kelvin on the other side of it. Okay, so this is the heat from engine block that is cooled by the glycol, and glycol gets that temperature, that heat at 370 Kelvin, and it transfers when its temperature is 350 Kelvin to air. Here you will have the air. Okay, and for the air part, it receives the heat at 350 Kelvin, and it ends at 298 Kelvin. This is the system. Now the question says that find the generated entropy inside the coolant, inside the engine block, and in the radiator air combination. Okay, so we will need to find the S generation. Okay, so we will do it one by one. So we will first start with the engine block, and then we will move the glycol part and the air part. Let's do it. So the first, the engine block. So this is the CV1, and then we will have the glycol part. This one will be that CV2, and then you will have air part. This one will be that CV3. And these are the three components that we will analyze it. So, and we will assume that the first one is that we will assume it is steady. This one is a very important assumption here. And the second one actually is not assumption, but it is the real case. All of them are closed. Okay. Closed system for the engine block. We are in then the closed system for the glycol. The inlet and the outlet are included here. And for the air also, we are assuming that this one is closed system. Okay, so the air part can be open system, but let's assume that we have the closed system here, and we don't have any inlet and outlet, and these are just the temperatures for one step. Okay, let's solve it now. For the engine block, firstly, so if I write the second law here, second law says that the change of entropy of the total system, so that's change of entropy actually of the system will be equal to that total in minus the total out plus the generation part. Okay. And when you work out with this one, you will have the units of joules by Kelvin. In the question, it is given as kilowatt, or the rate of it. Therefore, I will write this one as the del S by delta T of the system will be equal to that in with dot here minus out the dot here plus the generation the dot here. Okay. This one will be watt by Kelvin. I will work out with this part instead of that one because the units given in the question are in watt units. And for the engine block, I've said it. So all of them are steady. It is written here. It is steady. Therefore, this term goes to 0. And for inlet, you have the mass. For inlet, you have the Q dot mass dot. Sorry. For outlet, you will have the mass dot. For outlet, you will also have the Q dot and generation part. Mass flow rate is 0 because it is a closed system. The engine block is closed. We are talking about the surface. There is Q dot into the system, which is 2000 watts. And there is Q dot out of the system. These two are there. And the generation term is also. So it will be that 0 will be equal to 2000 watts divided by the temperature when it receives for the engine block is 430 Kelvin. This one is the inlet minus second one, again the same, divided by the 400 Kelvin. Because it is steady system, steady means that this Q dot is the same. Here also it is the same Q dot, 2 kilowatts. Here it is also 2 kilowatts. And here it is also 2 kilowatts. It is a steady system. It is very similar to electric current. You have the same amount of current. And here you have the same amount of the heat flow. And plus the generation part. Okay, rate of generation. So you will have the generation part will be equal to this one, 400 minus the second one, 430. And the final result, I will just write the final result, it will become that 0.35 watts by Kelvin. Okay, this is for the engine block. Now I will do the same step for the cooling agent, which is the glycol. It will be that glycol system. Similarly, you will have this one is the glycol. For the glycol, one side you will have the 370 Kelvin. The next part you will have the 350 Kelvin. You have the same amount of the heat, which is 2000 watts. You have the same amount of heat here. So that if it is, you will have the same equation here. If I write the second law, you will have the del S by delta T. Due to units, I'm dividing by delta T. So it will be that in minus out plus the generation part. All of them are rate quantities, therefore I'm putting dot here. So if you have this part will be 0 because it is steady, similar to engine block. This part for the mass, you will have 0 because it is closed. You will only have the heat transfer here. Similarly here, the mass transfer will be 0 because it is closed. And you will also have the heat transfer and the generation part. So if I write it for the final step, it will be that 2000 inlet divided by 370 minus 2000 divided by 350 plus the generation. And from here, the generation term will be equal to 2350 minus 2370. And you will have the result as 3.1 watts by Kelvin. This is for the second system. Now comes the third system, which is the air part. I'll write it here. You will have the third system, which will be the air. For the air part, you will have again the same system here. You will have air. And on one side, you will have the temperature, which is 350 and the 298. 350 Kelvin, 298 Kelvin. Okay. And I will write this similarly, the second law, which is del S by del T of the system, will be equal to total in with the rate quantity here, minus total out with the rate quantity here, and the plus generation with a rate quantity here. This term is 0 because we have said it is steady. And the in term for m dot, it is 0 because closed. Okay. And for the q dot, it is there. For m dot, again 0 because closed. Q dot, it is there. Generation is there. So then you will have that 0 will be equal to 2000 divided by 350 minus 2000 divided by 298 minus 2000 divided by 298 plus the generation part. If you solve it, you will get the generation part will be equal to 2000 divided by 298 minus 2000 divided by 350, and that one will give you the final result as 0.997 watts per Kelvin. And then if you add all of it, you will get the final generation of the entropy. Okay. So with this one, I have also finished the entropy for the entropy balance, okay, non-conservation of entropy. So the next lecture, which is the next set of examples, which is about the isentropic efficiencies. So this will be a different lecture, so I'll stop here. So I will prepare a next set of lectures for this one. I'm stopping the recording now.